So I promise you to take through some advanced GAN topics, and that's basically going to be old history, new history. First part is the old history because I have old slides, and the only new history because some new slides have been added. Okay, so this is basically this slide right after the slide we stopped last time. Day we were study regarding transfer by optimal transport, and then this is where you stopped. And I am going to divide different kind of GANs because you will often hear names of the GAN models and then source code and then therefore it's maybe beneficial to be familiar with. I will not dig very deep into the details. I'll just familiarize these terms and then inputs and outputs and what they can do and what are the general ideas. In that regard, I'll break down in two parts. One is the image GAN, means that no condition being used, and the conditional GAN by name condition being used. So in image GAN, one of the first GAN was proposed by Goodfellow et al. And this so happens that Goodfellow was at a bar enjoying his drink, and suddenly something kicked him, and then he went home that evening. In 2 hours he implemented this particular code and it was working. That's how the story goes, that this particular network had been implemented, network that does adversary. So funny enough though, that when there are some of the occurrences, one of the most famous game theorists, John Nash, because GANs also use the game theory approach. He was also at the bar drinking some drinks. That means you have to go bar more often if you are working on game theory or something related. All right, so this one does not involve convolutions. It's fully connected GANs, and actually the paper is quite nicely written. It's definitely worth reading, and especially the last part of the future works is very well done. There they already imply that conditional GAN can also be trained in similar manner. That's I think the first bullet points of the future work. But whenever you implement the GAN, okay, we end up implementing the GAN of DC GAN. Let's go again. I guess I'm going to give you the examples of DC GAN, but the GAN Goodfellow has been highlighted. Okay, this is going to be DC GAN. So DC GAN basically introduces the convolutions and then also transverse convolutions. You might have already studied about transverse convolutions. Basically, some sense the opposite operations. If you want to go from low dimension to high dimension, you will be using the transverse convolutions. And this is basically the generator, few lines of code. By now you are familiar already. I'm just trying to show you by the example code to prove a point, and mostly to encourage you to look into the code and play around, because these things may look scary until you start playing with the code. They are not that scary, except that running models on Colab can be very frustrating. All right, so this is the discriminator, and then this is the DC GAN that uses the binary cross entropy to classify whether an image is real or fake. And then here you basically pass the images through the discriminator. Then standard protocol that you pass the noise from the generator and pass the fake image to the discriminator, right? So this is here you are passing the real images through the discriminator. Here you are generating the images, you are generating the noise here, and then you are passing the fake images here, and then you just combine the cross entropy, and then you have got the loss for the real, loss for the fake, and just back propagate, and your implementation GAN is mostly over. So 4 snippets is all you require to implement this GAN. Therefore, feel free to play with basic GAN model, and you can start training by rather small data sets, and it's going to be fun and many things can be played around. All right, so this again is basically using these transpose convolutions for generation, and that's I'm putting it there. It was the first GAN was proposed in 2014, and 2015 this GAN came along. And most of the times when you are doing tutorials or when you are learning things, you often implement DC GAN, not the original GAN itself, because the power of convolutions. So if you are using the cross entropy loss to classify whether it's a real or fake, then it's considered not to be good. It ends up having so-called the mode collapse problem. So mode collapse basically means that once the discriminator one discriminator figures out what is real and what is fake, generator fails to generate anything that looks like real. So it's just like they are not playing the game anymore. Basically, the devil has been captured in some sense, or the discriminator really figures it out and generator fails to fool. There have been many tricks. One of very quite important trick is instead of using this cross entropy loss, you basically use Wasserstein distance. Wasserstein distance is just a big word and fancy things. If you look into the code, that's the only way to understand. It's just that you predict this, some predictions of max scores, or just between 0 to 1, and just minimize the distance between real and fake. So when you look into the code, it's embarrassingly simple. Wasserstein GAN, just, well, one side is maybe because it had to be theoretical rigorous to prove that what has been done and how far is it in theoretical ground. But on the other side, it's just to make it look fancy. But really what it does is, instead of computing the cross entropy, you take the mean, the average of the real, the scores of the real, and you take this is the average scores of the real, and this is a fake already, right? Generator gives you fake given the noise. There is the noise. They call it critic instead of discriminator. For its own reason, this is the average of the fake, and average score of the real and average score of the fake. The expected score of the real and the fake, they must be the same. So just take the mean, subtract, and treat that as a loss. And that's how it gets implemented. Most of the GANs use Wasserstein distance. It has own probabilistic meaning. We don't go much deep into details, but if you ever come across with Wasserstein GAN, before reading the paper, look into the code, because that will really give you the confidence, because paper is going to be lots of theory for its own reason, but the code is going to be super simple. So progressive Wasserstein GAN comes with a more curriculum learning point of learning. So curriculum point of learning is that you gradually introduce the difficulties on doing things, just like it happens in the schools, right? So you just ask your generator to do nothing more than generating 4x4 images. If you want to go very high resolution images, you can start by having these low resolution images, and you have very few layers of generator and few layers of discriminator, and then you can keep on adding the layers so that it generates a more and higher resolution. So you can progressively add the layers of the network, and so as to generate higher and higher resolutions, and hopefully also more and more details on those high resolution images. That's how it's just the training protocol. Everything else remains more or less the same. This is the work of 2018, and this is one of the example sets I showed you in the very beginning of whether it's real or fake of these GAN images. So that means this was also a turning point where people themselves used to get fooled that, okay, now we cannot really distinguish whether the generated faces are real or fake. So one step further, one of the famous GANs is the style GAN. Style GAN brings this idea of having this style encoder separately and then injecting that in the different layers. It's more about the advancement in the architectures, that how the content and the style needs to be treated. And then so in the images that you can see is that, let's say if you want to generate a person wearing a tie, and then based on that if you have some kind of semantics, let's call that more of a content, then we have not yet decided about the style, right? It has to be Persian, it has to be Thai, it has to be all, many other things, but who should it be? What should be the color of the tie? What kind of tie should it be? And so on and so forth. Those aspects of the person, like what kind of is the person wearing the glasses, having thick eyebrow, sharp jaw lines, and so on and so forth, right? So all those things come in the side of the styles, and those can be represented differently than the content itself. Then that way it becomes easier and it just learns better, and those things can be encoded differently than that of the content, and that's basically the idea. This is a very nice architecture, and it works for both conditional, unconditional GAN, and it's more popular for the unconditional case. And you can see these images. Now this particular GAN goes much beyond just the human faces, because if you think about that, human faces have a quite consistent and continuous distribution, right? And then often these images are quite well aligned, and therefore one can argue that learning on human faces is rather easy. But if you take the examples of these cars and then bedrooms, these are difficult images to learn. And the style GAN was one of the first GAN that actually now start making you ask the question that if the picture of the car is real or not, because previously the progressive GAN was just about whether the pictures of the human faces were real or not. So style GAN made it even more realistic. These are the images generated by style GAN, and they look really, really real. So that way, here you can see that you can now play with the what does it mean by style, and you can now play with the generation. You see these fine and coarse details, all things being encoded across different dimensions. It's more about subjective viewpoint. You can understand that what's been changing there. Anyway, so far that was more of the GANs in the unconditional settings. In the conditional settings, instead of giving no Z as an input, you also give a label as an input about what do you actually want, right? So if you want a dog, you ask for a dog. If you want a cat, you ask for a cat. And then at the same time, you also give it the discriminator that you want it to learn the joint distribution of the image as well as the label of the image Y. And then basically just the inputs are going to be different. Instead of just having one input, you have two inputs, both for the generator as well as the discriminator in theory, and then how you inject that particular conditions and so on and so forth would differ. Here, Y is not only the image class, rather it can also be the description of the image, how do you want it to be. So here the conditioning is done on the skates on the top. This is using the pix to pix conditional GAN. This basically translates pixel by pixel. And then this is the sketching, and then you can generate the shoes out of it. You can give the Google map view, what do you call it, satellite view. You can go to aerial photo, map to the aerial photo. This is difference in the style, and then you can just compare pix to pix and pass it through again and generate using pix to pix. So in this case, if you want to translate one to the other, you need to be able to supervise pixel wise. So problem comes is that I have a bunch of images of horses, and I want to make them zebras for some reason. Or I have a bunch of images of I don't know, mountains in the winter, and I want to make that look like summer. Then I may not have the pairwise supervision, so then data is bound to be unpaired, right? Then what do I do? Here you can see the paired example is that you have got this kind of one, and is the ground truth of the other for the translation. Whereas here they just random images. You might have bunch of images, one from the Leonardo and one from Van Gogh, and you want to translate this style from one to the other. So you can never have this kind of pairwise supervision. So what you can indeed do is that you translate anyway to the one domain to the other, and then pass you the discriminator and say that if it is from that domain or not. That may not do a super good job. That way you have to make its back, translate it back, and do the something called cyclic consistency. So the idea is that here you might have, here you might have the horse, and you have got the zebra. So you just load a generator that learns horse to zebra, and then this actually learns to basic discriminate whether it's zebra or not. And then you take this zebra image and take it back into the horse domain, and then say that, okay, once I make the whole cycle, it must be the same image all over again. That way it maintains the cycle consistency, and turns out that is super useful to be able to translate this particular example. You see here, this is the horse can be translated into zebra. This is the summer image. No, this is the winter image can be translated to summer images. So that's how you can translate, by maintaining the so-called the cyclic consistency, and that's what the cycle GAN uses. This way, if you want to go from the one domain to the other domain, you have to train two models, right? One to go there and one to come back. But then if you have many more, then you cannot do that anymore. Therefore, you can train something called star GAN. Star GAN, basically here the idea is that instead of having all these tiny blocks, are the different model that you would have trained to go from one to the other. So instead you can just train much more less number of models by conditioning them, and then having more of the common shared space. So that's how the star GAN does. So the star GAN, the trick is that if you start understanding from here, it's instead of just saying that it's already real or fake, it also say that which particular domain it comes from. So that way you can actually have one generator that not only takes the input image that it needs to translate, but it also takes the target that it needs to take it to. So that way you can do the style transfer of this one particular person. All right. So that one particular person, this is the input image, and then you can change the color, gender, age, skin, and so on and so forth for these set of images. That's the star GAN. And star GAN was not powerful enough, and then bunch of researchers at Google decided to make a big GAN. It was really big. They decided to train that on the whole ImageNet on 1,000 classes. And let's see what happens in 2018. And so it turns out that they uses so much of resources that actually, well, arguably there exists no GAN or GAN-like models. They are as good as Big GAN, which was trained in 2018, and that's a big thing in deep learning community or modern machine learning community. That's something that's been established in 2018 has not been defeated, and this is mostly because that I mean, at least in some sense not been defeated. It's mostly because that Google has lots of TPUs, and that's how these images been generated. That looks super realistic. Now we went much beyond faces, right? Much beyond bedrooms, much beyond cars. Now it's like all the classes of ImageNet. That's how crazy it was in 2018 already. These are all conditional by the classes. If you want to go beyond the classes, sometimes you do. Interpolations. So then one of the conditioning takes form in the form of the image segmentations. Let's say, since you can take an image and do the segmentation, you can also do the opposite process of taking the semantic mask and generate the image. That also takes in the form of the conditional GAN. It's just a Y of the other form, and then it's just more about how do you inject that in the form of the conditioning. That's what has been done in this particular paper of Spade, published in 2019, where the input you can see on top. These are the inputs, and these are the outputs here. That I think it better illustrates. Okay, so then the way it's been injected, the way Spade works is that you can inject your semantics in different labels, and it's not that fancy. It's just that it just gets injected in instance normalization fashion, and that's pretty much it has some architecture that's been proposed. I guess that's not very important for now, because if you want to get the more details, I encourage you to look through the paper. But the idea is to take away is that you can actually condition by using the semantic map of an image, and then you can actually control the image accordingly. Here you can see this is how the Spade operates.
Our interactive application looks like a simple paint app. However, instead of color palette, we have semantic palette. Let's pick a label and use the fill mode to replace cloud with ocean.
On the top is a sky.
Some cliff rock will be nice. Interactive application. Our interactive application looks like a simple paint app. However, instead of color palette, we have semantic palette. Let's pick a label and use the fill mode to replace cloud with ocean. Some cliff rock will be nice. Let me make the scene more interesting by adding a small rock and a faraway mountain. You can apply different styles to the image by regenerating the style code or by stealing styles from guide images. We continue drawing by adding a small beach. Trying different styles or trying different semantics. It's all up to you. This time, let's draw some mountains and trees. I first draw a grass-covered hill in the foreground, and then mountain in the back. More cloud will be nice. How about we plant a tree on the hill, like this? Note that the same label renders into two visually distinct objects, the trunk and the leaves of the tree. Now let's change the season. Even though we simply replaced grass with snow, our image generator did more than that. The tree leaves are gone, and there's now snow in the back mountain. If we go back to grass, the snow in the back mountain disappeared. Now I'm gonna draw a small pond on the grass. Look at the reflection of the tree on the water. Our method enables everyone with or without artistic skills to express their imagination. Please visit our webpage to learn more. Our interactive application looks like a simple paint app.
So one of the GAN that you also may hear often enough is also the scene GAN. Scene GAN basically exploits or uses only one image to generate. So there is only one training image. So I also actually showed you in the teaser very beginning day before yesterday that there were images, they don't even use any image to learn, right? And there were networks doesn't use any real image to learn, and this will actually uses only one image to learn. So this is to show that what all kind of priors about the images that you can use to generate and modify one image itself. And then that's those priors that this particular GAN uses to generate slight variation of the images. This doesn't have audio, so you fine. It does, but so you can see that things are moving there. Somehow figures out that given one image, what can move, what all variations can be generated. So of course, one must not expect too much because it just learns from one image. So it gives you some realistic variations of that. This one, for example, this is quite a lot of variations, right? It's just learning from one image. I think one of my favorite is this. This is the training image and it just makes fire, dynamic fire. It is quite realistic. All right, these are this is also conditional GAN because it learns upon one image and just learns to modify it, right? All of these. Anyway, so there's where the old history and then recent history I introduce is a few scary version. One of them in the form of the knowledge transfer that you can actually train your GAN on your ImageNet. And then this is the GAN train on ImageNet. And then you can actually transfer that GAN train on the ImageNet onto your dataset. This is this picture doesn't exist in ImageNet. So basically, now if you want to make your own GAN, then you don't have to train it from scratch, and it does work quite well if you take the image that train GAN and then do the transfer learning. So the way is that does the transfer learning is that if you have I think if you want to generate a panda from a bear, then it just somehow figures out that how the knowledge needs to transfer from the bear happens if it bear happens to be there in the ImageNet, then it realizes that it can borrow very coarse level information from the bear, whereas the details maybe need to be borrowed from something else. This is the another conditional GAN. That's borrowed for the transfer. This is the another conditional GAN that helps you to do the modification of human emotions in a continuous way without requiring the continuous labels. These are very subtle changes that you can change the human emotions that doesn't even require all the labels of the human annotations for the human emotions. So you can see that you can take a baby. Now we are going exactly on that realm where images start now looking the deep fake, because you just took the picture of the baby and then make the baby kind of cry in a very subtle way. It looks quite realistic and preserves the identity and everything. So that's the manipulations of facial images already in the realm of deep fakes. And then it goes way beyond that. Now you can generate images by the description, and this is called DALI. The model has not been released. Results have been released by OpenAI in 2021, and the way it's been generated is that you give a text description saying that you want an armchair in the shape of avocado, an armchair imitating an avocado. You give one or the other, and then there exists nothing like this, right? There exists nothing like this. It has seen only the chairs and the avocado and other things, of course, whatever exists. But when you give a description that you want armchair in the shape of avocado, it somehow figures it out, and then it looks realistic, no? So it's a fun as well as scary, the way you perceive. So these are the other set of images that I actually showed you in the very beginning, that these kind of images can be generated even without requiring any real image. So these are all because that we are just testing out. Wow. So that what does it take to understand the image by generating, right? And then sometimes one is even asking that, do I even need any image to generate any image, right? Can I generate images or modify images based on one image, small amount of data? Can I do the transfer learning? All these kind of questions, they remain open, interesting. The whole idea is that what I need to do or what can I do to be able to understand by generation or vice versa, right? So that what exactly is an image in many regard. And this particular paper is in that sense that what is a real image, right? And then I might have lots of examples of synthetic images, then would that suffice me to generate real like images, or at least learn the distribution of those real image batches, and hopefully will be useful somewhere else. These are the recent advancement. Then I can quickly go through the promises and the changes. That the promises are that now you can use these images for image super resolution or image enhancement. You can take images from your cell phone and make them look like images taken from DSLR. And most of your smartphones are not capturing the images that you see. Actually, they are already been post processed. Those processing often are already done using deep networks. They learn within this similar framework, especially if you have Google Photos. I know you do. And then it tries to understand, not only sometimes it recommends with the enhancement, those enhancements been done using the neural networks, which have some form of GAN like training or architecture. You can see here examples that that you can enhance. One is before and one is the after, from top to the down. Top is the result, inputs, and bottom is the results. So in that sense, what you are essentially trying to do, just to connect back with the storyline we had before, is that you have got images of, let's say, so bad distribution of the bad image, and then you can generate or modify the distribution of these bad images so that it looks like the good images. by simply having the target images of this form, because see, so I have these kind of not so good images in its own terms, and you want to enhance by mimicking the distribution of the good image, because you never have actually example image that what is good. No, you don't have the exact pairing what is good. What you actually have is that what are the good images. You only have the example these good images, you have these images that you want to translate to. You're just mapping the distribution of your not good images into the distribution of the good images in the sense of the enhancement. So similarly, you can do super resolution by having these low resolution images. You can upscale into high resolution, and then there also that you can use generative frameworks. Here you can see that so ground truth high resolution images should look like this. If we just do simple bicubic interpolation, this is how the image looks like, and this is the results of one of the GAN based super resolution method. You can also use GANs for image compression, that if you are using compression such that it still looks realistic at the end when you decode, then with the very similar compression ratio you can get left half of the image. Whereas if you use the traditional method, it looks pretty bad, and therefore you can also leverage adversarial training or GAN like architectures to do the image compression. And many artists have used GANs for artworks. They are quite fun, and there is a song, the music actually generated by GAN. There are also that actually lyrics generated by GAN. I think this one is actually the music being generated by GAN, whereas the lyrics is given to it. And so those kind of artworks, and this is some modern arts, if you understand, or I don't at least, but this is a modern art in some form that you can do using GANs. And this is the audio. Let's not play it now. So you can find it in this OpenAI junk box, that you can actually play and listen to them, and they sound pretty okay. You can use generative networks again in medical imaging. These are some of the results where if you try to do the reconstruction of MRI by having the undersamples, so then if you reconstruct, if you don't have enough sufficient samples, then if you reconstruct, then in traditional way reconstruction will look like this. But if you use the learned framework, then the reconstruction will look like something like that. This means that you can have much quicker acquisitions, because you don't need to have so much like in the classical methods. This one is on the CT scans. Okay, the list continues. You can also use in augmented reality, where you dictate that what you want to render just by giving this information about the depth and the semantics and the materials and so on and so forth of the object, and then that can get rendered onto the image, so that you don't have to use the classical methods to render them, and you also don't need the textures, and you don't have to worry about the lightning and so on and so forth. All these things are here. Just a video that you can render like this by using the GAN-like framework. Okay, it's not all good. Of course, there are bad things about giving power to people, right? Then one has to be aware of it. And then I will also discuss about the dangers of GAN. Maybe we can stop here and take some questions. I also need to go quick to finish early enough, but I would be happy to take some questions here now, if anybody has any question. Right, it's only me speaking. Okay, there you go. Can you pass that? Yeah, sure. Well, biases in their own regard, they are good and bad. I don't know which particular context of bias that you're talking about. Yeah.
Biasness can be like reduced or like how they're affecting the applications we are making, but are there no implications to it?
But I think some of the difference would be is that since I am presenting the slides, I am pro GAN, right? And somebody who's talking on the other side might not be pro GAN. So I don't see so many problems with the GANs. I mean, not that they might have immediate problems, obviously, but they can also be resolved by bringing the tools that they use on the other side if necessary, right? So regarding the biases, I don't know which particular context of the biases you're talking about. Is it in regard to generating the captions? Is it regard to generating the images? Yeah. Oh yeah. Basically, you will not have as much control that you could have it otherwise, right? Basically, he's just purely unstructured, data-driven based. That okay, whatever it gets examples that you have given, that it tries to basically rely on heavily on the data. Therefore, it has huge amount of data biases, right? And whereas on the other side, you can have much more better control. One of the example is this, that if you are collecting lots of images, let's say in ImageNet, it's ImageNet is full of dogs and cats, right? And there are very few rare animals. And then if you want to classify these rare animals, then it doesn't do good job. Because data is bound to have some sort of bias, right? Doesn't mean that you cannot fix the problem. If you know where are the biases, and from the data you could possibly have, then you can resolve them, right, by having more class balancing. Let's say this is one of the technique, right? But if you don't have those kind of extra tools to address, then the networks are bound to fall into just minimize your loss and whatever the loss is destined to do, right? Similarly in GANs also, that you don't have much of the control, just throw the data and then ask it to figure it out, right? And you're just learning the data distribution itself without necessarily having any kind of control, right? If you go in the GAN in the primitive settings without that particular control, then GANs are indeed expected to learn the data distribution if that happens to be biased for some classes or some semantic tags, then that's what is going to happen too. So it just does not consider in its primitive forms. That doesn't mean that it cannot be improved, because I'm here to defend right now. Anyway, anything else? All right, so the dangers are that this paper is a recent paper, and it says that GAN generated images are surprisingly easy to spot for now. And that's for now part is the most dangerous. So it turns out that you can actually train classifiers to classify whether it's a deep fake or not. The problem is, of course, it's going to have domain gap. Then if you have not seen that particular kind of deep fake, then it doesn't do good job. But the problem is that it's whether deep fake or not is a binary classification problem. Even if you have 70% accuracy or 90% accuracy, it's not that great. So of course, manipulated, modified, easily modifiable techniques and the images can be used for malicious uses that you might be aware of. and then how they can be used, and how we can design methods. They can detect, avoid, block, and all those kind of malicious practice is also something that one has to be aware of. So that's I already showed you some of the examples that what you could do, and here are more examples in regard to having lip sync in a way that you can make somebody speak in the videos by syncing the lip, and hence you can make all the people believe that something one has never said actually been said through the video by making these deepfakes. Of course, it has both side of the applications, on the good side and bad side. Maybe you can just play this one and some other stuff.
Hey, Vsauce by Cloud here, and this video is going to be really by Cloud here, and this video is going to be really weird, eerily, you might say, but surely it looks unusual. Some of you may have already noticed, but this is not a mere coincidence, and the reality is, and AI is behind what you are seeing right now. It uses my voice to lip sync the face in the video, and what's different to deepfake is that it's using sound instead of another face to generate lips movement. You can read up their official paper called "A Lip Sync Expert is All You Need for Speech to Lip Generation in the Wild," short for Wave to Lip, if you are interested in the details. But let's just say you can do basically anything related to lips and audio generation, of course. With just an audio clip, you can use it to sync up with the videos of your choice, and just with a quick render, you will get something like what you are seeing right now. In a way, basically dubbing over the video along with the change of lips movement. Isn't that useful? Well, and a bit concerning. Anyways, there are still a lot of functions that we can look forward to. For instance, there's a lecture in a language that you do not understand. With a translated audio dub, you can easily use this AI to lip sync and watch it like they actually speak the language of your choice. The same goes for movie or sports dubbing. It is also as easy, but the quality of this definitely still needs some improvement. In some cases, you can see the blurry mouth shape or the replaced image outline. Like this clip I just played. This not only can be helpful for dubbing, but also animate CGI characters. Remember how badly some auto-generated facial expressions and lip syncing in some games can be? Well, this could be one of the potential solutions. Another really interesting implementation is that it can be used to generate cutoff or disrupted video calls while the audio is still going through. May look a bit creepy though, just only seeing someone's mouth moving. Last but not least,
ダメだねダメよダメなのよあんたが好きで好きすぎてどれだけ強いお酒でも歪まない思い出が
yes, memes, everyone's favorite internet entertainment. From making the whole Reddit dumping Uturnian, or maybe simply make your friend chuckles, it is definitely a fun future go-to for the fellow memers. To easily play with this AI, I'll link a collab and a tutorial of how to use the collab down in the description. If you enjoy my work, you can consider supporting me on my Patreon so I can make my mom proud and to continue to make more of these videos. Thank you guys for watching, follow me on Twitter, and join my Discord if you haven't, and I'll see you all next time. Hey, Vsauce.
जिन्दगीमा एकपल्ट महिला हेरेन भने जुनसुकै विकसित देशको जोसुकै मान्छे होस् जोसुकै धनी होस् गैँडी देखाएको छैन भने
It's good. Okay. So I think I will skip through some slides because I also promised to finish early. So with that, I just request you to participate with the Q&A. If you have any question, please feel free to ask again. Any question? Okay, please. So the person one in the middle is actually Goodfellow himself. So Ian Goodfellow, who was the one who drinking at the bar. That's the guy.
Hello. Yeah, my question is from the earlier session. What I wanted to ask is, in self-supervised learning, we're just comparing the downstream tasks and seeing that which method is learning better compared to the other. But the approach we're training is, we're simply comparing the labels in supervised, while in self-supervised, we're using different kind of pretext tasks to learn the representation. So do you think that only comparing the downstream tasks is enough to say which one is learning better, or any other metric should be required?
Well, comparing on many downstream tasks seems to be the only way to know whether we are doing it right or not, right? Maybe doing only one is not sufficient. The whole idea is that you can somehow represent all the necessary visual concept in some low dimensional embedding, right? There is representation that can easily use for, and it is in the vision context, that to solve pretty much all visual problems, right? And then if you are using that for many visual tasks, and then if it works in like good in many visual tasks, and I think that's the only way of knowing that it is working or not. So to answer your question, with one, that's kind of a proxy that maybe it's working, right? If you have more than one, with same embedding solves to more than one, that would be better. That's why if you actually see that some of the papers are actually just not doing image classification, that's the accuracy to show. They also do object detection, image segmentations, and other tasks too. And there also it seems like these representations are indeed useful. Does that answer your question? So you can just without the mic, you can ask, like, otherwise if it's not working.
What I was thinking is, like, maybe just the intuition is that maybe SSL methods, they need to be, they are more capable of learning, because we're not just limited to some set of labels. So maybe some, like, only comparing the downstream tasks might be not enough to.
No, I think this is, it's more philosophical, right? That in any scientific framework, that a hypothesis can only be validated by experiments, and there's no other way, right? Similarly, also that you may actually obtain the most amazing visual representation that you would never know, right? And if you cannot ever know, then it's just having some kind of theory that never been tested yet, right? Like something like string theory, maybe, that you cannot test it, you cannot know it by experiments, then within the scientific framework, that it's not that valuable except for its beauty. On the other side, that something that really is valuable is that the experiments comply. Then what all experiments we can conduct and then validate there is when it becomes meaningful, right? Otherwise, it's not that one is questioning that it happens to be even better than what you can evaluate. The problem is that without evaluating, we cannot know. So only way of knowing, right, from the scientific framework point of view, is that you conduct experiments and evaluate that whether it's useful or not for the vision task. At least the way I see. And therefore, more downstream tasks, better it is, right? But then you also exist through, I mean, how much can you exist through the downstream task? And there are some standard downstream tasks, and that's what everybody is and evaluating. And at some point of time, it also, even the evaluation itself becomes standard benchmarking, that you evaluate on certain setups so that other people can compare against you and everybody, because you cannot even fully trust yourself, you only experiments, because others should be able to reproduce, right? So in that settings, that you try to reproduce others' experiments and then report in the same setting. So that's how you also being limited. So if you are just keep on expanding the number of tasks, then everybody should be able to reproduce the exact same thing, right? Therefore, you limit yourself into like 3-4 tasks, and everybody does the same experiments over and over again, so that you can be more confident with the outcomes. So they are like problem on both the sides. And to answer your questions, that sure, more downstream tasks, better it is. And the way I say is downstream task evaluation is the only way actually to really know if it is, if we obtain good visual representation or not. Yeah. Thank you.
Thank you.